Hello and welcome back. Well, I'm glad we made it through the empty rectangle video because today we're going to talk about one of the veritable superstars of any Sudoku puzzle. I'm talking about by-value cells. These little things are one of the most powerful, versatile, and useful tools we have to solve even the most diabolical puzzles. So let's take a closer look and see why. Now, just for today's lesson, to make it easier on me, I will sometimes use an abbreviation for by-value cell, so I don't have to say it in full each time, okay? Let's call it a BVC. Got it? BVC equals by-value cell. I might still say by-value cell here and there sometimes, but just know that whenever I happen to say BVC, it will be short for by-value cell, okay? Great. A by-value cell is one in which there are only two remaining candidates, two possibilities. Like you see here, these are all by-value cells. This means that in each one of them, one of the two candidates must be true and the other must be false. This is exactly the primary characteristic of a conventional strong link that we learned about in video number 3. This relationship is also the same as that of a conjugate pair, but the two candidates in a by-value cell are not called a conjugate pair because they are two different digits. Don't forget that. The two candidates in a by-value cell are not called a conjugate pair, even though one must be true and the other must be false. The term conjugate pair only refers to the last two remaining same-digit candidates within a house. Like these two 7s because they are in the same row, or these two 3s because they are in the same column, or these two 5s because they are in the same block. These are all conjugate pairs. We will take a closer look at conjugate pairs in the next video, video number 19. But back to today's business. There is a conventional strong link between the two candidates in a BVC, but as I said, they are not called a conjugate pair, so don't make that mistake. As we know, in an AIC or alternate inference chain, where the links must alternate strong, weak, strong, etc., a strong link can be used as a weak link because it has the properties of both. This means that within any BVC, there is both a strong link and a weak link. The two candidates in a BVC are strongly linked and they are weakly linked. This means that not only can we say if either one is false, then the other one is true, but we can also say if either one is true, then the other one is false. This is because they cannot both be false and they cannot both be true. One must be true and the other must be false. The fact that this internal link can be either weak or strong comes in very handy when you bump into a BVC in the course of constructing a chain of any kind, because you can use that internal link as whatever you want, weak or strong. You can always make a link between the two candidates in a BVC, but in order to make a link outside the BVC, you must always make the link to another instance of the same candidate from which you are leaving the cell, and it must lie in the same house, like this. Like if you are leaving this colored cell from the 7, you can only make a link to another 7 in another cell in the same house, i.e. within the same row, column, or block. It does not have to be another BVC. It just has to be another instance of the same digit candidate in another cell within the same house. Like you can link this 7 to this 7, and that would be a strong link because they are the only two 7s in block 8. Or you could link this 7 to this 7, and that would also be a strong link because they are the only two 7s in row 7. Or you could link this 7 to this 7, and that would be a weak link because there are more than two 7s in column 6. Or you could link this 7 to this 7 up here, and that would also be a weak link. Because you are coming out of this cell from the 7, you cannot link it to anything but another 7 in another cell in the same house. Whenever you are making a link from one cell to another cell, The link must always be between two instances of the same digit candidate, like from this 9 to this 9, or from this 9 to that 9, or from this 6 to this 6. But you cannot link this 6 to that 6, or this 9 to that 9, because they do not lie in the same house. Now, the only way you can link two different digits is if they lie within the same cell. Now, don't forget that. I know I keep repeating this, but it is of the utmost importance. Like you can link this 7 to this 3, okay? But you cannot link that same 7 to this 3 over here because they lie in two different cells. And all these rules apply to both weak and strong links. And we are talking about conventional links as described in video number 3. There is an effective strong link between the two endpoints of an open-ended AIC, but this type of link is the result of the logical inferences of the links in the chain, unlike a conventional link, which must be a direct link. So with an effective link, the endpoints do not necessarily have to see each other or be in the same house, although they can be. They just don't have to be. Capiche? All right, here in this puzzle, we have an AIC type 1 that begins and ends with bi-value cells, and we're going to start up here, and that's a strong link from the 1 to the 3. Then we have a weak link down to this 3, and then a strong link to this 3, and then a weak link to this 9. Now I'm going to have to use something else here. Otherwise, my links are going to interfere with each other. And there's a strong link from this 9 to that 9. Then there's a weak link from this 9 to that 9. And finally, a strong link from this 9 to this 1. So our starting point is the blue 1 in row 1, column 9. And the ending point is the yellow 1 in row 3, column 6. Now, there is an effective strong link between those two candidates because if the first one is false, then the last one is true. Or if the last one is false, the first one is true, and that's by virtue of the chain, because they do not see each other. They are not in the same house, but still there is a strong link between them, and we call that an effective strong link. Okay? Now, when you have two different digits that lie in two different cells within the same house, the two cells can see each other, but those two candidates do not see each other. This is an important distinction. Like here, we have an AIC type 2, and we're going to begin on this candidate 9 up here, and that's a strong link to the 5. Then there's a weak link down to this 5. Then that's a strong link to the 7. And then a weak link over to this 7. That's a surrogate weak link. And then we have a strong link up to this 7, a weak link over to this 3, a strong link to that 3, a weak link to that 3, a strong link to this 5, and then a weak link over to this 5, and finally a strong link up to this 5. So the starting point is the blue 9 in row 3, column 1, and the ending point is the yellow 5 in row 3, column 3. Now the two 5s in those cells see each other, and the two 9s see each other. But in the chain, we have an effective strong link between the blue 9 and the yellow 5 up there, but they do not technically see each other. The two cells see each other, but the blue 9 and the yellow 5 in row 3, column 3 do not really see each other. But there is still an effective strong link between them, which, as we know, allows us to eliminate the start digit from the end cell and the end digit from the start cell. And because these are two bi-value cells, we're going to solve both those cells. Now I'm going to have to get rid of these arrows. And so we can eliminate the start digit from the end cell, which is the 9, and we can eliminate the end digit from the start cell, which is the 5. So that means we can solve this cell for 9 and that cell for 5. Because those were bi-value cells, and because we make those two candidate eliminations, it leaves a naked single in each cell. And as we know, this is the best kind of AIC type 2 that you can find. And you should go out of your way to try to construct these because they are very, very productive. Please know that when constructing a chain, you can skip one of the candidates in the BVC if you want, and that would simply mean that you enter and leave the cell on the same digit like this. So let's say you were starting on this 3 over here in column 9, and you were making a link to this 3 in column 6. And then your next link could be up to this 3. You don't have to use the 7. There is no law that says you have to use both of those candidates in your chain. But if you are using both of the candidates in the BVC in your chain, then you have to be conscious of whether you are using that internal link as a weak link or a strong link, because that will determine the type of link on which you need to leave the cell. In other words, that will determine whether the next link in the chain needs to be weak or strong. In any chain or loop, you must always alternate the links, strong, weak, strong, weak, strong, weak, etc., because that is the only way you can make any logical deductions from the chain of inferences. Using the formal definitions of strong and weak links will produce a series of inferences from which we can analyze what's going on. So if you are calling that internal link a weak link, then the next link out of the cell must be a strong link. But if you are calling the internal link a strong link, then the next link going out can either be weak or strong because it only needs to be weak. It just needs to be the opposite of whatever the internal link is. Like if you enter this cell on a weak link and then make a strong link to the 7, then the next link needs to be weak. And so you could go up here, for instance. All right? But if you are entering on a strong link and use the internal link as a weak link, then your next link needs to be strong. It has to be strong. And so you could go down here, or you could go over here because those would be strong links. But you could not connect it to these two 7s up here in column 6 because those would only be weak links. If you do not use the internal link, then the links entering and leaving the cell will be opposite. Like if you enter on a strong, you must leave on a weak. And if you enter on a weak, you must leave on a strong. And if you are using the internal link, then the links entering and leaving the cell will either both be strong or both be weak. They will both be the opposite type of link than the internal link. Capiche? But here is where it gets interesting. If you are using the internal link as a strong link, then the next link in the chain, which will be the link coming out of the BVC, can be any link, weak or strong, because it only needs to be weak. So this really increases your options of where you can go next. If you are linking several BVCs in a row, and each time you are using the internal link as a strong link, then all you need to look for is another BVC with that common candidate, and you can connect it without having to examine it. You don't have to worry whether it's weak or strong. It can be either. As long as it's the same digit in a different cell in the same house, it will work. The strong links will all be within the cells, and the weak links will all be between the cells. Like this. Let's start up on candidate 1 in row 1, column 2, and make a strong link to that 7. Okay? And now we're going to make a weak link to this 7, and then a strong link to the 2, and then a weak link to this 2, and then a strong link to the 9, and then a weak link to this 9, a strong link to this 5, a weak link to that 5, a strong link to that 3, a weak link to that 3, a strong link to the 8, and then a weak link up to this 8, and then a strong link to the 6, and then a weak link over to this 6, and then finally a strong link to this 1. And so now we have an effective strong link between those two candidate 1s because they are the endpoints of this AIC. And notice that in each of those colored by-value cells, the strong link is within the cell and the weak links are between the cells. But when you get to the last cell, remember that when you enter on that weak link, you have to make the final link to the other candidate in the BVC, which here is the yellow 1. And when you make a chain like this, Whether you can make any eliminations or not will of course depend on what the endpoint candidates are and how they match up. And when you make an entire chain using only by-value cells, it is known as an XY chain, which we will cover in video number 28. Now here is a little brain teaser for you. Did you ever stop to think about how many different BVCs there are in total? What do you think the answer is? Well, let's figure it out. Since there are only 2 digits in a BVC, we know the answer cannot be 100, right? It has to be less than 100 because 100 is a 3-digit number. So you may guess the answer is 99. Do you think that's it? Wrong. There has to be 2 digits, so that means we can eliminate the numbers 1 through 9 as they are only single digits. So now you may guess 90. Do you think that's it? Nope. Wrong. There can't be any zeros because we do not use the digit 0 in Sudoku. So that rules out 10, 20, 30, 40, 50, 60, 70, 80, and 90. Another 9 possibilities eliminated. So now you may guess 81. Well, that sounds pretty good because Sudoku is based on a 9x9 grid, right? And each house must have the numbers 1 through 9, and 9 times 9 is 81. So, is 81 the answer? Nope. Wrong again. If you think a little harder, you will realize that the 2 digits in a BVC must be 2 different digits. This means we can rule out 11, 22, 33, 44, 55, 66, 77, 88, and 99. Those possibilities cannot exist. Another 9 eliminations. And that leaves 72. So is that the answer, you may ask? Well, if you guessed 72, that's a pretty good guess, but unfortunately it is still wrong. What you have to realize is that in Sudoku, 28 is the same BVC as 82, and 76 is the same as 67, and 93 is the same as 39. So this means that the answer is 72 divided by 2. That's right, 36. The correct answer is 36. Let's take a look at all of them and see why this is true. All right, here in this chart, let's take a look down the first column, and we have 1 paired with all the other numbers. And of course, it can't be 1, 1. So the first one is 1, 2, then 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, and 1, 9. That makes 8 by-value cells. Then the next column will be for the 2's, and of course the 2, 1 is already accounted for because 1, 2 and 2, 1 are the same by-value cell. And it can't be 2, 2, so the first cell in the column for the 2's is 2, 3, and then you have 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9. That's 7 more. Then for the 3's, it can't be 3, 1 or 3, 2 because they're already done, and it can't be 3, 3 because that doesn't exist, so you start with 3, 4. And if you continue on, you see that each time for each number, it's 1 less. So you have 8, 7, 6, 5, 4, 3, 2, 1, and that adds up to 36. Now, knowing this does not really help us in any way, except to make it a little less intimidating, I think. Anyway, I thought it was an interesting fact and wanted to share it with you. A bit of Sudoku trivia. That's all. In any event, by-value cells play a major role in a large percentage of the solving techniques that we will be learning soon. Here is a list of some of them to give you an idea. This means that you should always pay attention to how BVCs interact with everything else that's going on in any puzzle, and be ready to take advantage of their power. They are your friends. Okay, that's it for today, so let's go back outside and finish up. Thanks for watching. So now, I hope that you have a little better understanding of how by-value cells work, which will make learning the numerous solving techniques that employ them a bit easier. There is one more side topic I'd like to discuss before we get back to the main course, and that is conjugate pairs. Just like by-value cells, conjugate pairs are an important concept and tool that helps us solve puzzles. They play a very important role and are a vital component of a large percentage of all the various solving techniques. So we will take a closer look at them in the next video, video number 19. And I hope to see you again for that lesson. Until then, be well and be happy.